In this video, we'll review some of the common Laplace transforms of functions that we'll use throughout this semester. The first one we'll take a look at is the simplest function, which is a constant function. So f of t is a constant, a. If we put a into the definition of the Laplace transform, and we evaluate the integral, we find that the Laplace transform of the constant function is a over s. Next, let's do the same thing for the unit step function. The unit step function takes a value of 0 for all t less than 0, and a value of 1 for all t greater than or equal to 0. Our textbook authors use the notation capital S of t to indicate the unit step function. Please don't confuse this with the lowercase s, which is the Laplace domain independent variable. As an aside, in MATLAB, the unit step function is called the Heaviside function, and it's implemented with the word Heaviside. Notice that the Laplace transform doesn't care what happens before t equals 0. So the unit step at t equals 0 is actually the same as a constant with a equal to 1, because the unit step is constant for all t greater than 0. Therefore, the Laplace transform of the step function is just 1 over s. We could also change the magnitude of the step by multiplying the unit step by any arbitrary constant. And that would be the same as the Laplace transform of the constant function. Next, let's look at the Laplace transform of an exponential decay, e to the minus at. If we take e to the minus at and we insert it into the definition of the Laplace transform, we can combine the product of the exponentials by summing the exponents, and then evaluate the integral. We find that the Laplace transform of the exponential e to the minus at is just 1 over s plus a. Next, let's take a look at another piecewise function, the rectangular pulse function. This rectangular pulse function takes a value of 0 for all t less than 0, and then it undergoes a step at t equals 0 to a value with a magnitude h, where h represents the height of the rectangular pulse. At some t equals tw, which is the width of the pulse, then the rectangular pulse goes back down to 0. The rectangular pulse function has two parameters, h, the height of the pulse, and tw, the width of the pulse. To find the Laplace transform, we only need to integrate from t equals 0 to tw, because for all t greater than tw, the rectangular pulse takes a value of 0. Even though in the time domain, the rectangular pulse function is a piecewise function, in the Laplace domain, the rectangular pulse function is a continuous function of s. It's h over s times 1 minus e to the minus tws. Now we know we shouldn't see the variable t in the Laplace domain, so keep in mind that this tw is just a constant parameter. It's the width of the pulse, and it happens to have units of time. That's okay. Tw appears in the Laplace domain expression for the rectangular pulse function. This rectangular pulse function contains within it an example of a common feature that we'll use in time domain functions, which is called a time lag. In chemical and biological processes, one function is often related to another by some time delay. We saw an example of this in Chapter 9 when we talked about the signals coming out of sensor transmitters sometimes being delayed in time by a time delay theta d. Here we'll consider any general function f of t that's delayed in time by theta time units. So if our original function f of t looks like this, the delayed function looks identical, it's just shifted along the time axis. Now when we take the Laplace transform of a time-delayed function, we're also going to multiply it by a unit step occurring at t equals theta. We do this, again, because the Laplace transform knows nothing about f of t before t equals 0. So it doesn't matter what is happening to f of t before t equals 0, we need to set that part of the function equal to 0. So this s of t minus theta takes a value of 0 for all t less than theta, and a value of 1 for all t greater than theta. It's essentially a switch that turns f of t minus theta off before t equals theta and on when t is equal to or greater than theta. If we know what f is, and we know that f is related to f sub d, the delayed version of f, by this expression, then we can find the Laplace transform of f sub d, the delayed function. To do that, we put f of d into the definition of the Laplace transform. Then we integrate this in two parts. the part for t equals 0 to theta, for which our step function takes a value of 0, and the part from theta to infinity, for which the step function takes a value of 1. Of course, the integral for this first part is just 0, so it can be ignored. Next, we'll rewrite the exponential e to the minus st as e to the minus st minus theta times e to the minus s theta. Now, because theta is a constant, we can do two things. E to the minus s theta can be factored out of the integral. Remember, we're integrating with respect to t here, not with respect to s. Second, since theta is a constant, dt and dt minus theta are the same. A differential change in t is equal to a differential change in t minus theta. So we can perform a variable transformation. And we can define t star as t minus theta. When we do any kind of variable transformation on the independent variable with respect to integration, we also have to change the bounds on the definite integral. If we're now integrating with respect to t star, which is t minus theta, then the theta here becomes 0. Of course, infinity and infinity minus theta are the same thing, so the upper bound remains infinity. Now we can recognize the integral from 0 to infinity of f of t star e to the minus st star dt star as simply the Laplace transform of our original function f. So the Laplace transform of a time-delayed function with a delay of theta is e to the minus s theta multiplied by the Laplace transform of the original non-delayed function f. Whenever we see an e to the minus s theta in the Laplace domain, we should immediately recognize that the time domain function is delayed by an amount t equal to theta. Let's go back now and revisit our rectangular pulse function. Remember, we found that the Laplace transform of the rectangular pulse function was h over s times 1 minus e to the minus tws. H over s is the Laplace transform of a step of magnitude h, and minus h over s is the Laplace transform of a step with the same magnitude but opposite sign. Here, the second step, the one with the negative magnitude, is delayed in time by an amount tw. So the rectangular pulse function is really the sum of a step of magnitude h occurring at t equals 0, and then another step of magnitude minus h occurring tw time units later. In the Laplace domain, we see the sum of two step functions, one of which has a negative sign and is delayed in time.